Okay, so instead of trying to use ideal short circuits and open circuits to find the impedance or admittance parameters of a network, we're going to use real resistive terminations because they're easier to maintain at high frequency. So for instance, I could put a voltage source and send an incident waveform A into a network. Let's just say that the waveform is going into the network. I terminate all ports in the network that I'm not driving with a 50 ohm load. And then I measure the reflection B coming out of the network at whatever port. So I send a signal in and measure what's reflected out of the port. I call the input waveform the incident waveform and the output waveform the reflected waveform, and in general my S parameters, S is equal to B over A. So I'm just measuring the ratio of what comes out over what goes in. If I write this out in a matrix form, I apply my S parameters by my incident waveform matrix, and I would receive my reflected waveform matrix. So S times A is equal to B. In general, if I have an S parameter, Sij, I is the output signal reflected and J is the input signal incident. Also, we can convert to other network parameters, for instance Z and Y parameters, through well-known relationships that are available in many texts such as Posar. If we're looking at a parameter Sij, where J is equal to I, this is going to be similar to looking at a reflection coefficient, or gamma. If we're looking at Sij, where J is not equal to I, this is like a gain or a loss from one port to another, or a transmission coefficient. Now, it's important to note that these are not exactly reflection coefficients or transmission coefficients because they depend upon the source and load reflections. But in certain cases, we can treat these like they're reflection coefficients. For instance, if there isn't a lot of reverse transmission in a structure, or if the ports are terminated with conjugate loads. Now, what we want to begin to think about is how do S parameters relate to amplifiers? And in general, they relate to amplifiers as we can find things like the gain, return loss, isolation of the amplifier, and the reflection coefficient of the amplifier using S parameters. The gain of an amplifier we typically call 20 log 10 of S21. This would be the magnitude of S21 in dBs. Typically, it might have a parametric value of 15 dBs to 20 dBs, something along those lines. And it's important to note that this gain is not the total gain of just the amplifier by itself. This includes port reflections at the input and output. The return loss is sometimes called 20 log 10 of S11, or the magnitude of S11 in dBs. Typically, we want this value to be less than minus 10 dBs. This is telling us how much signal that's input to the circuit is returned to the source. So in other words, how much of our signal is not going fully through the network. Much like we looked at gain, we can look at isolation, which is reverse gain. This is saying if we were to put a signal into the output port, how much it would make it through back to the input port. And ideally, we want this to be a small number, something like minus 30 dBs. We can also find the input and output reflection coefficients, which relate to the port impedances. So our input reflection coefficient is equal to S11 plus the reverse isolation times the gain times the reflection coefficient at the output port divided by 1 minus the S22 times the reflection coefficient at the output port. And gamma out has a similar function, albeit we just replace gamma out with gamma in and S11 with S22 in the equation. It's important to note that gamma in is equal to S11 if the reverse isolation is perfect. In other words, S12 is equal to 0, or if the output port is perfectly matched to its load. In other words, S22 is equal to gamma out complex conjugate. The same is true for gamma out. Gamma out is equal to S22 if S12 is equal to 0, or if S11 is equal to the complex conjugate of the input reflection coefficient. A few other parameters of interest are the mismatch loss. The mismatch loss tells us how much signal doesn't get to the output because it was reflected at the input. Mismatch loss we can calculate at the input or the output simply by knowing what the reflection coefficient at the input or the output is. Okay, so this is basically telling us how much signal is lost due to reflection. If we know the mismatch loss, we can find the insertion loss in the device, and this tells us how much loss or gain does the circuit provide irrespective of if there are reflections at the input and the output. And in order to find the insertion loss, we just add the mismatch loss at the input and output ports to the S21 of the device. And finally, it's important to note that power amplifiers are dependent on both their bias level and their signal swing. And these network parameters that we've just discussed are called small signal parameters. We can do simulations that provide large signal S parameters where the S parameters are calculated around a periodic time varying bias point. But we do have to be careful when we start to use S parameters on devices that have large signal swings like power amplifiers, because they do diverge at large signal swing from what they would be at small signal swing.